Welcome back everyone. In this lecture we will continue with working with formal series, and we are going to see some immediate applications in solving linear recurrences. So, let us start with defining derivatives and doing some formal calculus on formal series. So, the most important message about working with formal series is that so whenever we are looking at formal series, let us say of the form f of z equal to summation a n z power n. So, the most important thing is all the calculations that we are interested in doing with this formal series. So, as far as that is actually those kind of calculations they are allowed in calculus, and whenever like let us say we want to talk about some identity proving like so the log of f of z and exponential of this, we want it to be again f of z. So, whatever they mean, okay, we will be defining those terminologies here. So, this type of identities, let us say we want to actually have it for the formal series, then one can ask when one can have such identities. So, these identities they are true as far as these identities are true in the actual calculus. So, whenever you are doing calculus, let us say over reals or complex numbers, and if we happen to have such identity for the real functions or complex functions which are defined using this f of z, and this identity let us say happens for all z in a very small open subset of C. So, this is just a open subset of C, and this identity is true. So, then one can expect, actually not only expecting, one can actually assume that such identity is true even in the formal series field. Okay. So, this can be actually formally proved. I am not going to actually do it in this first course or introductory course, but this is the like take home message that one can actually have for working with formal series. So, whatever identities that we are interested in proving or interested in checking among this formal series. So, we need to first see or check whether such identities are available from the calculus that we do it over reals or complex. Whenever we have it, so then we can actually borrow such identities in the world of formal series. Here in the world of formal series, like I said before, we are not actually indeed worried about any convergence and so on, but most of the time when we want to actually take for example infinite products, or we want to do some calculus on formal series like taking derivative or taking exponential or logarithm and so on, and we want such identities to be true at least for some very small neighborhood, okay, that should have positive radius. So, once we have such identity in the world of complex numbers or real numbers, so then we expect that kind of identity is true in the world of formal series. So, that is how actually one actually does all calculations in the world of formal power series. So, towards that let me just define some of the basic terminologies that frequently used in the world of formal series. Again many identities that I am not going to prove, but one can actually check them and verify these identities are true. For example, one can define what is called derivative of a formal series. So, let us define and then list all the basic properties that one sees in the first course of calculus. So, let us take this f of z. So, again warning is that this f of z they are not treated as functions. So, they are only treated as formal series. So, that means we do not talk about convergence and so on. So, there is no question about substituting some value for z here. Okay, that is the meaning of we do not treat them as functions. So, let us take f of z, which is given to be a formal series, that is an element of C double bracket z. So, then define the derivative of this formal series as follows. So, recall that usually the derivative of z power n with respect to z is defined to be n times z power n minus 1, and we are going to use that here in this series as well. And when for this, like all we are going to do, we are going to just use term by term derivation. So, we do not care about like how to actually commute this summation operator and the d by dz operator and so on, and we just define formally that the derivative is nothing but the summation n times a n z power n minus 1, where n is running over from 1 to infinity. So, this is the definition of the derivative of f of z. So, now one can rewrite this f dash of z as follows by reindexing. So, one can allow this n plus 1 a n plus 1 z power n, and then you just allow n to vary from 0 to infinity. So, this is another way to write this f dash of z. So, this is what the derivation means for the formal series. This is, you take it as definition. There is no question about convergence and so on. So, now it is easy to prove the following identities. Like I said, these identities are true even for real functions and complex functions. So, that is why you expect it to be true in the formal world. If you are seeing it for first time, it is better to prove all these identities. So, whenever you take the sum of two formal series and then look at its derivative, then we expect that to be sum of the derivatives. So, f dash of z plus g dash of z, which is true in the world of formal series. Similarly, when we take the product f of z g of z and then look at its derivative. So, recall that d f g over dz, where f and g, let us say functions in z, it is going to be df by dz times g plus f times dg divided by dz. So, this is the usual Leibniz rule of the derivative of the products. So, the same thing is true even in the formal series world. So, this f of z times z of z dash is going to be f dash of z g of z plus f of z times g dash of z. So, this is true. So, in particularly when you take the inverse of f of z and then look at its derivative. So, this is going to be minus f dash of z divided by this f square of z, and this can be proved using 2 that f of z times f inverse of z is exactly given by 1, and using that and using formal calculations one can prove that f inverse of z dash will be minus f dash of z divided by f square of z. So, okay, let me use this properly. So, what I meant to here is that this is the derivative and this is the square of the function. So, let us put the derivative here. Okay, this f dash is the derivative, this is the square, f of z square. And similarly, like one can actually define many formal series, they are actually coming from calculus, and then one can look at its derivatives. For example, one defines e power z to be the summation z power n divided by n factorial, n range from 0 to infinity. So, this is the definition of e power z. So, and this is very common exponential series that one studies in calculus. And similarly, one can define what is called log of 1 plus z, which is given by summation minus 1 power n minus 1 z power n divided by n. Again n varies from 1 to infinity, and these are all the definitions of these power series, or you can take it to be notations if you want. So, minus log of 1 minus z, which is most important one. So, this is exactly given by summation z power n divided by n, where n ranges from 1 to infinity. So, now given this, one can also calculate its derivative. The derivative of exponential is itself, that is known. So, let us do this exercise, that the derivative of the exponential is again the exponential. So, which is known fact in the calculus. So, I was talking about identities like this, which is true in the calculus world. So, you expect it to be true here in the formal series world. Similarly, the log of 1 plus z, the derivative of that is exactly given by 1 divided by 1 plus z. And more generally, one can actually prove something like this. If you choose f of z coming from C bracket z with the constant coefficient f of 0 equal to 1. So, then one can define what is called the logarithm of f of z. So, the logarithm of f of z is defined to be, so recall that you can write f of z as 1 minus g of z, because f of 0 is 1. So, now use this identity, okay, which is minus log of 1 minus z. So, that is the identity that we are going to. So, minus log of f of z is exactly defined to be the summation g of z power n divided by n, where n range from 1 to infinity. So, this is our minus log of f of z. So, now once we have this definition, then it's easy to see, or one can prove that the derivative of this is exactly given by f dash of z divided by f of z, and this is true in the world of formal power series. Okay. So, this is the definition of actually log of f of z. Now, using this definition, one can actually derive this equality. Okay. So, this is all I wanted to actually talk about formal series. And so, now what we are going to do, we are actually going to see an important application. It is indeed a classical application of this generating functions or formal series techniques. So, that is indeed solving linear recurrences with the constant coefficients. So, let us first look at some example, and then later we will actually generalize to general order k linear recurrences. So, first let us start with this Fibonacci numbers, how to solve them. So, let us recall what is the definition of Fibonacci. So, the Fibonacci series is, or the numbers are defined recursively using the following recurrence. So, we start with f naught being 0 and then f 1 being 1. So, then f n will be defined to be using the previous coefficients f n minus 1 and f n minus 2 for n greater than or equal to 2. So, this is how one defines the Fibonacci numbers. What one is interested in getting a closed formula for this f n. So, not only that, one wants to actually see how it grows and so on. Okay. So, what is the closest number that can be lies closer to this f n. So, that is the question that we want to actually answer. If you think about it, it is not very difficult to prove these f n's are all natural numbers. So, using induction, one can easily prove that these fn's are all natural numbers. So, my question is how to compute them, okay? How to compute fn's or get closed formulas for them. And there are many techniques one can actually use in order to compute Fn. So, the two important techniques, one is using these generative functions and then getting some closed formula for Fn, and then another one is using matrix theory. One will be able to construct a matrix which is 2 by 2 matrix, and then by diagonalizing that matrix we will be able to get closed formula for this Fn. But in both techniques solving polynomial equation will be very crucial. So, let us look at this first technique that uses generating functions. So, in order to compute this Fn, so individually one can easily see that the difficulty will grow when we are interested in computing this Fn individually. So, it becomes very difficult task, but this recurrence suggests that instead of looking at them individually, one should look at them in a group. Okay. So, that is where this generating functions comes in handy. So, you look at this formal series which is having the nth coefficient as this Fibonacci number Fn, where n is varying from 0 to infinity. So, now we have this formal series which is an element inside our CZ. So, now using this recurrence that we have, that Fn is equal to Fn minus 1 plus Fn minus 2, one will be able to actually rewrite this f of z as follows. So, you rewrite f of z equal to, so this recurrence starts with the coefficient from n greater than or equal to 2. So, note that f 0 is 0 and then f 1 is 1. So, we rewrite this f of z as follows. We rewrite this as z plus summation n from 2 to infinity f n z power n. So, now what we are going to do, we are going to just kick out this f n and then replace this by f n minus 1 plus f n minus 2. So, then this equation becomes z plus summation f n minus 1 z power n plus summation f n minus 2 z power n, where first sum is running over from 2 to infinity, second sum is again running over from 2 to infinity. So, now we will rewrite this summation slightly. Let us first look at this first summation, which is summation f n minus 1 z power n varies from 2 to infinity. Now, you just subtract and add 1. So, you just reindex this n minus 1 starting from 1 to infinity. So, then we can easily see that this is exactly given by, we can take out z and then this becomes f n z power n, where n now runs over from 1 to infinity. Note that f naught is 0. So, one can actually just put n equal to 0 here. So, that means this first summation can be rewritten as follows, z times f of z. So, this is exactly z times f of z. And similarly, the second summation can be rewritten as z square times f of z. So, this gives us that f of z is given by z plus z times f of z plus z square times f of z. So, this is what we have. So, now what we can do, we can use this equation and then collect f of z one side. If we collect f of z one side, then we get 1 minus z square times f of z equal to z. So, this tells us that f of z is indeed given by z divided by 1 minus z plus z square. So, we got a closed formula for this generating function that counts Fibonacci numbers. So, now this equation indeed very important. So, this uses this polynomial 1 minus z square into the denominator. Now, using partial fractions, what one can do? One can rewrite this as sum of two geometric series. So, let us try to do that. So, let me just give what happens in the theory. So, by writing this quadratic equation 1 minus z minus z square equal to 1 minus alpha z times 1 minus beta z. So, then we can see that f of z can be written as z divided by 1 minus alpha z times 1 minus beta z. So, now what one can do? One can use this partial fractions form and rewrite 1 divided by 1 minus alpha z times 1 minus beta z as follows. This you can rewrite as some a divided by 1 minus alpha z plus b divided by 1 minus beta z. So, one can explicitly find alpha, beta, a and b. So, I will actually leave that as exercise. So, if we do the calculations, you can actually verify that. So, this I will leave it as exercise, that a is given by alpha divided by root 5 and b is given by minus beta divided by root 5, where alpha is nothing but 1 plus root 5 divided by 2, which is the golden ratio, and beta is given by its conjugate 1 minus root 5 divided by 2. So, this is easy to check. So, now let us use this form and then rewrite f of z. If we rewrite f of z, we get that f of z equal to a z divided by 1 minus alpha z plus b z divided by 1 minus beta z. Recall that one can write 1 minus alpha z as summation alpha power n z power n range from 0 to infinity using geometric series. So, now if we substitute this here, we get f of z equal to summation a alpha power n minus 1 plus b alpha power beta power n minus 1 times z power n, where n range from 0 to infinity. So, this tells us that f n, which is the coefficient of z power n here, which is exactly given by a alpha power n minus 1 plus b beta power n minus 1. If you substitute back the alpha, beta and a and b that we have given in this exercise, so you can actually reduce from this that f n is exactly given by 1 divided by root 5 times 1 plus root 5 divided by 2 power n minus 1 minus root 5 by 2 power n. So, you can see that we have obtained a closed formula for this Fibonacci numbers using this technique. But the drawback of this technique is that this root 5 we know only approximately what it is, and it actually kind of computes at least for large n's that so where this f n should be lying, because if you think about it for all approximation purposes, this 1 minus root by divided by 2, this is indeed less than 1 by 2, because 1 is greater than root 5. So, that tells you that for large n, this 1 minus root 5 divided by 2 power n indeed tends to 0. Okay. So, that means f n is indeed closer to this 1 plus root 5 divided by 2 power n. So, of course, we need to multiply by that 1 divided by root 5. So, if you write it properly, this is you take this 1 divided by root 5 power n. So, this is the kind of approximate value for Fibonacci number for large n, and which is not very clear from the recurrence relation, but this powerful technique suggests that this should be the case, which is indeed very interesting. So, one can also use matrix theory in order to actually solve this recurrence. So, maybe I will just indicate how one can approach this computing Fibonacci numbers using this matrix theory. So, we will rewrite this recurrence using matrices as follows. We take this recurrence, and then what we can do, we can actually rewrite this recurrence using this matrix A. For example, if we take this matrix and then if we compute the matrix multiplication of this G1101 with this Fn minus 1, Fn minus 2, then what we get is exactly given by Fn and Fn minus 2. So, maybe we can reverse this, take this to be 2, this to be 1. So, then we get Fn minus 2 plus Fn minus 1, which is Fn, and then we get in the bottom we get this 0 plus Fn minus 1, which is Fn minus 1. So, using this, one can actually start with this basic vector which is given, which is 0 comma 1, and then we repeatedly apply this A. So, then we can see that we will be getting actually that recursively all the elements that we are interested in. So, that means computing Fn becomes computing this A power n. So, the problem of computing Fn reduces to the problem of computing A power n. But this is not indeed some easy problem to handle, and this is where actually the notion of diagnosability and so on, that is more helpful. So, if we know that A is diagnosable, then we can write A as PDP inverse for some diagonal matrix D. So, then A power n will be same as computing D power n, which is easy to do, because if D is some lambda 1 lambda 2 diagonal matrix, then D power n is very easy to compute, which is lambda power n 0 0 lambda 2 power n. So, for diagnosable matrices, at least we have a hope. So, finding this larger power of A is reduced to finding this invertible matrix P and this diagonal matrix D, which is somewhat easy problem, at least in this case. Okay, it depends upon the characteristic polynomial of A and so on, and this is what actually motivates us to look for diagnosability, because for diagnosable matrices it is easy to compute its higher powers modulo if we know how to diagonalize them. Okay, which is actually somewhat easier problem than computing this powers of A, which is very difficult problem in general. So, this is the common technique that is used from linear algebra to approach the same linear recurrence problems, but we will not take this approach, because I do not want to assume the knowledge of linear algebra in this course, but we will as we have seen, so we will use this power series technique in order to approach this problem. So, that is much more efficient and somewhat ground to earth. If you think about it, more or less both the methods actually uses basic linear algebra in the background. Maybe I will explain that when we are going to see the very general statement about solving this linear recurrence of order k. Okay, so I will stop here and then we will actually start with solving general linear recurrences in the next class. I will stop here. Thanks.